Hello everyone, welcome back. So today we'll be talking about transmission and actuation, and at the end we also try to conclude the course today. So first I start with the actuations, and what we learned that most of the time with the actuation we also talk about the transmission, and if we try to look at different kind of transmission system, what we realize that the screw threads are one of the very important invention, and it can provide very large torque, and that's the reason it's used in many of the machines. So what we realize, like you can, it's very simple. So a screw thread, if you see, and so if you just turn it and so you'll turn it and there will be translation, and what you can see is a design of a power screw here. So we might have seen lady screw. It's a use in the machines, and mainly used to convert rotations to linear motion in various actuators, vices, presses, jacks, lead screw on lathe. So you can see it's widely used, and one of the reason is why it's used so often is the large mechanical advantage, and that's the reason it's used to lift or move large loads, and used for power transmissions. So there are two types you see more often these days. So lead screw, most of the time we are aware of, but another is the ball screws. And what you see, the lead screw, this is one of the example you see here, uh, used in the lathe, and this is used to move a nut attached to the load. It's a very rugged, and that's why it's used in many of the machine tools. But what we observe that there is a sliding motion, so a lot of friction, and the efficiency is of course relatively low, 30 to 50% depending on what kind of thread we are using. And if you look at the design, what you realize that the construction, the how we are going to place a lead screw or ball screw, the different elements right from the motor, then we have the linear bearing carriage, and we have this screw, and you can see the nut here, and lead screw here mentioned. It's also moving on a linear bearing rail, and then you have the flexible coupling. So one has to be aware of these elements, and I think by now one would be able to understand why all these elements are there. So what has happened? So the power screw, the lead screws, very good, and it's a use for power transmission, but the efficiency is very low. And what the researchers in Japan, Germany, what they have realized that, so if you look at the lead screw and the bearings, what if it can be combined, and that give rise to the ball screw. So actually, instead of the nut and thread, right, it's sliding on a wedge. Now there are balls, so it's a spherical balls embedded just like ball bearings, and now there is a rolling motion. So now you get the advantage of both, and because of that the efficiency has increased, and it's more than 95%. So very good, and at the same time it can be used to move very large loads. So it can, the efficiency is very good, can be used to move loads. And the sliding contact between the screw and the nut is now replaced by recirculating ball bearings. There is a point contact, and that is the limitation, because there is a ball and the thread, the contact is point contact, and of course then we have to understand and we have to also know how we select the bearing. So likewise, when we select the ball screws, we have to also take care of that. Nonetheless, what has happened, because we have not eliminated but reduced the friction part, it can be used for precision application. So precision machine with very high efficiency, they can use ball screw. So these days, very often in mechatronics application, in robotics application, or and even in precision application, you see this ball screw together with the rotary motors are very often used. But remember, there is a still friction involved, and what we understand that if friction is involved, there will be issues related to virtual play. The hysteresis will come into the picture, and definitely depending on the application, and if we are really going for a very high precision application, then we may have to think and we may have to find some other means. So this is the construction we just discussed, and from kinematics point of view, if you just try to look at it, this is the rotation you give to the ball screw, call it a spindle here. And if you check the nut here, the translation and the rotation along that axis is related, and through the pitch of the screw or the lead. Mm. So one rotation will move by one depending on how many starts are there. So usually one start, so you will get the lead will be equal to the pitch of the ball screw. What you have to do is you have to constrain the motion of the nut, and that's why it's attached to a carriage. So you have the nut here and then the carriage here. So the carriage can only move back and forth. So the rotation is getting constant. So since the rotation is getting constant because of the carriage, which is moving on the linear guide here, so it can slide easily, but it constrains the rotation. And since it's a constraint, so when we turn the motor, it will start moving back and forth, and it can give a very good resolution and precision as well. So of course, for precision, we have to look at some other aspects. So this is how it works. Of course, the alignment and the offset of the two, the motor and the linear guides and the ball screw axis, we have to take care, and that's why we need a flexible coupling here, and that we have discussed in the lecture. So now I think by now we should be able to understand the requirement, and we should be able to address all those issues one by one. So these are some of the examples and the detailed image of the ball screw. Many times the inside we don't see, but you can see there are a lot of recirculating balls inside. So as we turn, it recirculates, and so if we don't recirculate, what happens, from one end it will come out, so it has to be again moved. So that's why you have these tubes at the end, so it will again feed in the end. So this is one of the cut section, the section view to show the details. And that is the reason when you are moving at a very high speed, and if there are a lot of clearance, if you are not using a very good ball screw, you can hear a lot of noise. So that, and those are the things you have to look at, and depending on the application, you have to select ball screw, right kind of ball screws. So these are some examples. So Misumi is one of the uh, company, I think, where you can buy all the precision components. With respect to Misumi, what one may say that uh, they may not build the entire machine, but using the components from there, you can select, and you can assemble, like, and you can make your own precision stages for your own application. So you can see the ball screw here, and these are the linear guides. Of course, here is the precision is the friction is still involved. It's sliding, but even in linear guides, you have a different kind of where you have the recirculating balls, and then the friction can be reduced. But still, there is a contact. Be aware of that, and because of that contact, the friction, whether it's sliding or rolling, the precision will be lowered. So this is one of the, if you look at or search for precision motion stages, many times you get with the ball screw, and with the rotary motor attached to the end. So it rotates, and you get the linear motion. So it's a stacked, so it can move this way, and therefore this can also this can move in this way, and therefore you can have the two xy motions one should be able to get. You can also see that there are guides here, linear guides again. So I think one should be able to understand and figure out what kind of elements are there, and how it's stacked, how it's assembled. So one of the thing what we realize that it's very difficult to get rid of backlash, and one of the reason is when we have these designs, we provide some clearance so that uh, the assemblies can be achieved, and it's very difficult to get a perfect mating. So there will be always some clearance, and because of that there will be a backlash. And what we understand, if there is a backlash, there will be huge error. So of course the hysteresis is there, but backlash together with the friction, stiffness, what we understand that the hysteresis is really bad. So the overall backlash or play will be very large, and therefore we have to find a way to address that. And many times we use preloading to address backlash or any kind of clearance we have. And so preloading is used, and was used mainly achieved using some kind of a spring. So some examples you see, and so you split the nut and then preload them. So preloading is used for ball screws and lead screws and many other relative motion machine elements. So this is one of the way, and there are some examples here. So you can use tensile pretensioning here. We can use compressive preloading. You can have two section, nut A and nut B, and in between you have a spring element. So you preload so that there is always some contact. So how to get it? Yes, is uh, something that has to be calculated and addressed, so that the contact is defined and is always there. If the external force is more than the preloading, then it will ruin and then will get the backlash. So one has to be aware of. So there are few designs. So how to preload nuts in this kind of carriages. So what you can see, this concertina bush we have discussed earlier, and so we can use the this kind of flexures, and one end can be connected to the carriage and the other end can be connected to the nut, and this way we can get a preloading and we can get a backlash free kind of actuation. Similar concept is used in case of gears also. So how to get rid of backlash because of the clearances, and so two sections and preloading is used to get rid of the backlash. So the concept can, we can see that there are two pieces and they are preloaded, so they have a contact on the either ends, and there is always a contact because of the preloading. So what we understand that any actuation we talk about, they always come with the transmission, and there are many kind of transmission. We have not talked about that, but maybe one can refer to that. So yeah, for rotary we have gears. For linear actuation we have talked about the ball screws. There are capstan drives, there are pulleys, there are friction drives. So it always comes with some kind of transmission, and moment we have a transmission, they are bound to have some kind of backlash, and associated stiffnesses will be also there. So many times it's difficult to address those errors, and in a very high precision application, one try to get rid of that and try to go for direct drives. And that's why we talk about linear motors these days. So if it's for very precise application or very high speed application, we use direct drive. So there are other kinds of direct drives also, piezo actuations, voice coil actuators. But here we are talking about normal linear motors, just to give you an idea what kind of actuators can be used. And so here the concept is very simple. You have the rotary motors, rotary actuators. Just cut the stator and make it flat, and the secondary rotor is again flat. So if you put it in this way, then actually we can directly get a linear motion. So earlier, or more often, the we use rotary motors because of the availability. We can find it easily. The cost wise is also very low compared to linear motors. So one try to use rotary motors, and we can use a transmission. But of course, if you want to have a direct drive and want to get rid of those issues, we may like to go for linear motors. And this is one of the area what we find that we are heavily dependent on foreign inputs. We have to buy from US, Germany, Japan, Taiwan, right? So because it's used in those precision motion stages. So if we can have our own, it's a very easy to implement, and definitely we can get the cost benefits, and the technology is very simple. Yes, construction wise it might be difficult because it requires different kind of assembly, and understanding the principles of precision machine design, I think is possible to build this kind of linear motors together with the entire motion stages here itself. So this is now the coil, and this is the my motor or the magnet track in a U shape. So it just moves. So you can see that depending on the requirement, depending on the stroke, you can have a very large to very small stroke, and it's a direct drive. So the linear motors are one of the essential component and widely used, and it's available. I think there are more and more companies now building these kind of linear motors, and if we understand, then it's very easy to implement and use in our designs. No need to use rotary motor only. So I have shown it when I was discussing about air bearing stage. So you can see that the linear motor is here, is embedded in the design itself. But you also observe that we use air bearings, so air pads. So here everything, the linear guide is supported on air bearings, and the drive, the actuation is from the linear motor. So what you realize that the granite table, and the slider here, there is no physical contact between the two. It's actually floating on air pads and guided, and the linear actuator is providing the necessary actuation, the force required to move it. What you one may also see is the sensing part. The encoders are also there, so you have the linear encoders, and these days you have a very high resolution encoders you can find, and it can be used, and then using a proper controller we can achieve very high precisions. So this is how it looks like if you try to find or search for any kind of precision stages or air bearing stages. The granite table, that's one of the base material because of its rigid and firm, and more resistance to temperature, humidity. So this is widely used, and you can see the linear motors here for this direction, and you can have a same way here as well. So here you see again no contact because it's supported on air bearing. So you can see here you hardly see any kind of guides. So it's guided by this surface and this surface opposite to that, and on air bearing. So it's a floating, so it can move very freely. So friction is not involved. There is no backlash. The actuators, the linear motors, they are driving it directly. So whatever is the characteristics, we know and we can control it. So the control effort required to precisely move these stages is also minimized. So, and that's the reason these are these kind of systems are used for very high end application, for very high precision applications. Yes, linear motors are used in other application, but what you realize that in this case you are still using these linear guides, so which are friction based. So of course, depending on the application, it can be done. You can match it and use it. So again, direct drive, but then you have the linear guides. You can also notice the linear encoders here, so you can get the feedback, the position. So these are the some commercially available precision stages, and I think understanding all the concepts what we use to develop precision motion stages or precision machines, I think now one should be able to decode it, also reverse engineer it, or even develop stages for our own applications. So there are many things, the actuation, sensing, there are again materials. So one course may not be enough. There are many things to discuss. So this is just a start. And we have talked about the basic ingredients, the fundamentals. So what I try to do in the next 10-15 minutes is try to talk about different examples, how we use these various concepts and develop different modules, not the entire machine but different modules. Yes, we intend to design a full scale setup also, and maybe in due time we will be able to demonstrate. So I'll talk about few examples what we have done in these years in our lab with the students, uh, with the interns, with the visitors, with the scientists coming and working with us, and even with the companies, industries who are interested to work with us. We have developed these systems and working with everyone. So I'll talk about some of the examples to just give you an idea and also try to summarize through some of the examples. So this is I have discussed earlier. So for the medical device application, we talked about the actuation module, and just to get a, an actuation, linear actuation, without getting affected with the misalignment and offset, how to connect so that we don't have to really align the two axes. So we have discussed that, and we use the folded sheet flexure and bellow flexures, and we developed this. So actuation module. We also talk about the force sensing module, and we can develop uh, load cells or force sensing modules for any number of degrees of freedom. So here is 6 top, but depending on the application, if only suppose 4 or 3 is required, then it can be designed accordingly. And what we have observed that the simple looking elements like wire flexures uh, can help us in designing and decoupling the different force components, and we should be able to use the concept of exact constraint design and kinematic design, and then use the compliant mechanism to achieve the force sensing module. And we developed it, and we also try to include some other features for safety. So this is how it's done. So this is the setup. So force sensing module you have, this is the actuation module, and this is the for the tip measurement. So yes, again here, like we wanted to have a non-contact type of measurement. So what kind of method we use, we have discussed already. So I'm just trying to summarize, and this is how it looks like. So right from measuring the tip motion using the laser displacement sensors, using a cam, and then air bearing to support the rod so that the friction is we should be able to measure the force only in the tube, not because of the support, and the whatever the actuation force there, it can be measured. So that we can see. We also talk about air bearing motion stage, and how the linear motor and the air bearing stage is designed. So even the we talk about the structure, the how to get stiffness, and the how to preload these air bearings, and one by one we put the linear motor everything together, and we were able to get a precision motion states. What I also wanted to highlight is kind of methodology, kind of infrastructure required for this kind of setup. So for characterization, we need the interferometry, this kind of setup. So of course, with time, the size, the cost, it gets reduced, but it will be required. We further use these concepts and try to address some of the limitations what we have observed in some of the flexures. So for instance, in sheet flexures we have some issues, so we try to modify it. And what we realize that okay, we can have we can twist it for larger rotation, so we can extend. But at the same time, because of the shortening, so once we rotate, there will be shortening. So we are able to find a flexure based transmission systems from rotary to translation. So this is one we presented in USPEN conference. Similarly, in our lab also develop single DOF compliant rotary joint for large deflection application. So again, based on sheet flexures, and one can start with the kinematic design and understanding the degrees of freedom and constraint. We understand how it works, and we can further use FEM and try to find the range of motions and also the stresses, and we can further develop it and proof of concept. So this we are developing and trying to use it for applications for environment where we can get rid of normal bearings. So this is one setup we develop in our lab. Similarly, we also use flexure based screw mechanism. So you translate and you can get a theta or vice versa. So it's a back drivable, and but you realize that the folded leaf springs, folded sheet flexure, very good mechanism, and we if you provide in they are, if there is a offset and the fold lines are not intersecting and placed in a certain way that it provides you the screw motion. So we try to arrange, and again we can do the FEM and see ourselves what are the stiffnesses values and what is the range of motion. And using 3D printing, we can also print it and test it ourselves. So many designs and flexure based, we understand is elastic mechanisms. So it's a repeatable, and we can get rid of friction related hysteresis or backlash. So so wherever we have a small range of motion, we can have a very good repeatable motion. We can get a very high resolution and can use them for high precision applications. So what we realize that we can use these concepts. So we are almost at the end of the course, end of the lecture. So just trying to summarize. So the design principles, what we have covered in this course, and one may need to practice and use them. So degrees of freedom and constraints, we need to understand it thoroughly, and how we can get rid of if there is any over constraint, how we can eliminate. We can use those basic principles, and if we have to design anything ab initio from the start for our own application, understanding the requirements from kinematic point of view, we can start working using these concepts. We understood what is the importance of exact constraint design in precision, so we look for that. And Yes, there are some workaround, and so if there is a point contact, how to eliminate that, how to convert into equivalent design. So for that, we also talk about different kind of compliant mechanisms. So there are some standard compliant mechanisms, but we can also design our own. There are different kind of flexures which can be used. And what we understand that these compliant mechanisms, they are elastic mechanisms, so they are repeatable, and we can get rid of hysteresis, we can get rid of frictions, and we can get monolithic design. So it means not only for the precision, but if you want to miniaturize and want to make smaller machines, smaller devices, so the limit is only in the fabrication, whether we can make things to that scale. If we are able to make to that scale, it means using this concept, we should be able to make those things. And no wonder if one day we are able to make robots which can even go inside the body and can move and can swim in our bloodstream and can do the diagnosis and treatment. So the use of compliant mechanisms, we understood. We talk about different cases, different kind of compliant mechanisms. We also try to address why friction is bad for precision. Yes, friction is good for damping, but for precision it's really bad. Even if there is no clearance, we still have a backlash. We still have virtual play because of the friction and the limited stiffness of the system. So how to eliminate that, how to address that. So we talk about combined motion, how we can combine the different motions and we can get rid of the effective frictional friction force. Uh, Air bearings are one of the key components if we are going for a high precision application. And one of the reason is there because the friction we can eliminate, or the value is really small. So we talk about different kind of air bearings, the orifice type, the porous paths, and we understand there are limitation, there are the gaps, but uh, we should be able to address that, and we should be able to make things on our own. So air bearings, one of the key enabler. Linear motors are something we need it if we go for direct drive. So again, this is a gap and we need to address that. And we also talk about dynamics and control, and not only the precision, but we also want to go for high speed. So when we have such applications, how different kind of a step input, position, velocity, acceleration, or the jerk or the backlash, how it affects the system, that's something we need to understand and we need to address. So we try to give an idea how a precision machine looks like, what are the concept, what are the basic principles to design these kind of machines. And I try to show some examples and give you an idea how to design. So with this, we are coming to an end, but one thing what I want to convey that this is just the beginning, and we may feel like we can do now. Yes, we can start well with this understanding. We can design things, we can make the things as per our requirement, but this is just the beginning. More we do, more we learn. It's more about learning. And in this journey, I think I'm also there. So you can contact me anytime if there is any help required. And So I'll try to end with the quote from William Shakespeare's play in Hamlet. There are more things in heaven and earth, Ratio, than are dreamed of in your philosophy. So it's just the beginning. And let's start building machines for our own use. Let's start making precision motion stages for our own application, for our own consumptions, for the semiconductor industries coming to India, for electronic industry, for our research institutes, for our own institute, academic institution to support research here itself. Thank you.